Hello. So in our course of education in school, we might have learned about the concept of momentum. It's a physical quantity which is described as the mass times the velocity of any particular object. So we have learned that when there is no external force acting on a set of bodies, then the total momentum, the total linear momentum should be conserved. So now let us try to see how it works in practice. So here we have a system of five objects, 5 metallic balls. And right now you can see that they are at rest, which means the velocity is 0. So right now the momentum is 0. Now let's see what happens if I give a little bit of momentum to one of the balls. So here, when I release this, it will travel with a certain velocity. So it will have a certain momentum. And let's just observe what happens next. So what we are seeing is when it collides, it transfers its momentum to that object, and then it transfers back to the other one, and so on, until the last one. And then the last one gets that velocity and it travels. Then gravity pulls it back in, so then it pushes it, and so on, the thing happens. So had we been doing this in space, where there is no gravity and there is no external force, this thing would have kept on going for eternity. But because there is friction and there is some damping in the strings, it will eventually come to a halt. So this is, we see the transfer of momentum and the conservation of linear momentum at play. And we might have observed something similar in our day-to-day life as well. An analogous example to this, which is more easily available example, is when we see the concept of angular momentum at play. So we'll show you now how that works.
So the analog of what Kunal have explained already about the conservation of linear momentum, we have the angular momentum. For that, we, instead of having velocity, linear velocity and mass, we consider moment of inertia. And instead of linear velocity, we talk about angular velocity, which is the velocity at which we spin.
So here we have an almost frictionless surface to mimic how it would be if she was standing, for example, on ice, which also offers very low friction. So now so she has a distribution of mass, which describes her moment of inertia. Now I'll give her a little bit of angular speed, the angular velocity, and then she will have some non-zero angular momentum. So let's see what happens. So you might have seen that she slowly starts to spin a bit faster when she closes her arms. Let's see this with a little bit more velocity, angular velocity. So I'll spin you a little bit faster and just observe what happens when she closes her arms.
So you're seeing when I close my arms, I spin faster. That's because of the change of the distribution of mass.
And due to that, when the distribution of mass changes, her moment of inertia changes. And now these two quantities need to be the same because there is no external torque acting on her. So to conserve that, her speed increases because the moment of inertia is decreased. So that the product is now still the same as before. And that's what the figure skaters do. So in essence, all the figure skaters are physicists when they are using all this understanding.